right, so we're glad to have you here. And this is the best audience you'll ever have. Because they ask good questions, speak right up, and so enjoy yourself.
All right, thanks. My name's Rod Adams, and I publish a blog called Atomic Insights. Had a kind of interesting and varied career. I spent some time in the Navy. I spent some time trying to start up a small company. Then that didn't work so well, so I went back in the Navy. Ended up retiring from the Navy in 2010. Worked for Babcock and Wilcox just down the road from 2010 to 2013, and then decided it was time to really do what I've always wanted to do, which is to write. So I write a blog, and I'm writing some other things to try to take advantage of some unusual academic background. I graduated from the Naval Academy with a Bachelor of Science in English, and then I was accepted to the nuclear power program, served as an engineering officer on board submarines, and then ended up getting a master's degree in systems technology. So I'm not really an engineer, but I played one in the Navy. I was the chief engineer on a submarine, so it gets about as close as I have. So I'm very pleased to be here, and happy to have an audience who has a questioning attitude.
Did you want somebody to stand up there?
If you wouldn't mind, if somebody would advance, I'd make it a little bit easier for me. All right, go on to the. Okay. So the first questions I want to start with some questions and get the audience thinking. Right now, let's see a show of hands. What's your current position on nuclear energy? How many of you are neutral? Okay. How many of you are people who oppose nuclear energy already? I won't be getting any comments. That's okay. How many support it without question? And strongly support it? Okay. Good. How do you feel about empowering human society? One of the challenges that we have in this country is there are a lot of people who really prefer for us to have less power. We prefer for us to go back to a past where we depended on the wind and the sun and wood as our power sources. How many of you are neutral about empowering society? How many oppose it? You prefer for us to go back to the past and reduce our use of things?
I don't think we completely understand what you're asking.
Okay. Well, the question is, do you want more power, or do you want people to have less power? Do you want people to stop using things, stop wasting energy, stop, driving big cars, those kinds of things? Or would you prefer to look around the world and say, there's a whole lot of people that have almost no energy at all, and they need to be brought up, and we don't necessarily need to push ourselves down to make that happen? So that's the question. Would you prefer more power or less power?
So energy power or, okay.
Okay, you guys remember, you're engineering students. Power is energy per unit time, right? So if you want to be powerful, you need to use energy fast. That's more power. If you use energy very slowly, you can conserve energy. You cannot get tired. You cannot go very far and go very fast, and you can't move very much dirt around. You can't build very much. Yes. Okay, that's a good answer. It does depend on the source. Some power sources are better than others.
And I think like, between kind of all of what she's saying, it's, I guess, the level in which you're using it. Because, like, for some things, the really well developed, it makes it very efficient.
Mm-hmm.
But, like, nuclear, I'm neutral because I've seen what it can do. I see the benefits to it. But the fact of the matter is on nuclear submarines, like back on Wilcox, the cells that go into these submarine motors, they last for 30 years, but then they're put into a concrete ground with no way to destroy them or to clean them up, and so they seep. And so it causes more issues just from getting rid of it.
Yeah, well, we'll talk about that as we go along. That is a perception that has been widely distributed. And then if, let's go on to the next slide. Oh, one move back for you. Okay. One of the other really big issues that people have, and there's some different ways to talk about it. The traditional way is calling it global warming. Another way is to refer to it as climate change. But for me, the most important thing to be concerned about is atmospheric chemistry change. Changing our atmosphere from having a certain percentage of carbon dioxide and other gases like nitrous oxides, sulfur dioxides, etc., and having the way that those chemistry changes affect us are actually a little bit unpredictable. We have some certain knowledge of trends, we can build some models, but we're not really quite sure what happens if we keep dumping 30 billion tons of carbon dioxide into the atmosphere every year with the planned intention of a business as usual strategy of continuing to burn more and more stuff and dump more and more stuff into the atmosphere. We're not really sure what all those changes are going to do. They may cause us to get warmer at certain times of the year. Sometimes they may cause us to get colder if it slows the movement of the jet stream around and causes this nice deep polar vortex on a regular basis. We've had 2 pretty cold winters in a row right now, although the average temperature over the whole Earth is going up slightly because we're retaining more energy. Another problem with chemistry changes is that by putting more CO2 in the atmosphere, more CO2 is being absorbed in the world's oceans. And those of you who've taken some chemistry know that if you dissolve carbon dioxide in water, you get carbonic acid. It doesn't make the ocean into a big acid bath, but it does change the pH just slightly. And a lot of the creatures that live in the ocean are balanced for a very specific range of pH, particularly things like coral and other creatures that use the calcium carbonates in the ocean to create shells. And so if you change the ocean's pH, you can change the balance, you can have a big impact on which creatures survive and which creatures get stressed. So global warming is important. Changing the weather patterns has a big impact, and other things that we're not quite sure of. We don't really know exactly what the specific pattern's going to be over time. There'll be some ups and downs, some changes, and over time you might look back and say, wow, things are a little bit different now than they used to be. All right. So if you think that's important, put your hand up. If you think it's not important, if you believe the people that say, we can dump all the stuff we want in the atmosphere, we're not going to change anything. Humans don't have the power to change the world's climate. Well, who says it's not important? Okay. And for me, although I'm not the same generation as you, I'm in the category of most important issue facing my generation. Because if we keep changing gradually our atmospheric chemistry, we're not sure what the results are going to be, and an awful lot of our built infrastructure may become unusable. And I'm not talking about just coastal cities and those kinds of infrastructure pieces, but some farms, well-developed farms, may suddenly no longer have the pattern of rainfall that they expected. They may no longer have the pattern of sun and clouds, and they may stop bearing as much produce as they used to. If we move, people say, well, we could just move further north. Well, if you move further north from the temperate zones, the amount of land gets smaller because you're going up in latitude on a sphere. So it may look like Canada's got a whole bunch of land up there, but if you go up there, you realize that that map that was stretched out is not quite as big as it used to be. So some of the areas of land that we have may change. Let's go on to the next slide. And for all those reasons, I am an unabashed nuclear advocate. Okay, I really want to share what I've learned about nuclear energy over the years, some of my own personal experiences. Unlike many people who talk about nuclear energy, I've actually hugged a reactor. Okay, I've walked around it. I've been inside a submarine. I've been in charge of making the reactor and all of its supporting systems work. I've had 40 people working for me whose job was to keep the reactor running and keep reliable power going to our submarine. The other thing about submarining is you realize very quickly that no other power source can operate reliably sealed up inside an underground or underwater submarine or even a sealed building. You know, if we had to go onto our emergency power source on board the submarine, which is a diesel engine, we had to get up to the surface and get some air very quickly and some way to dump the exhaust, even though the diesel engine was much, much smaller in capacity than the reactor. With the reactor, we could go and almost as far, as fast as we wanted. With the diesel, we were very limited as to how fast we could go. We could only go about 3 knots as opposed to greater than 20 knots, and we couldn't go very far before we run out of fuel and everything else. With the nuclear reactor, we could, in fact, power that submarine. I was on an older submarine, so our reactor only lasted 14 years and only drove a 9,000-ton submarine. I think it was something on the order of 500,000 miles during that time. Okay, so and then we had to, get the reactor replaced. That reactor, by the way, was about this tall and about this big in diameter. Okay, that was the total amount of fuel we carried on board. The reactive mass, the uranium-235 on that submarine, weighed a little bit more than what I did. When we removed it from the submarine, we shipped all of our reactors to a single building in Idaho. All of the Navy's reactors, from the USS Nautilus to the most recently decommissioned submarine, have all been transported to Idaho. That's where the used fuel is. It's in a single building with a pool that's a little bit smaller than an Olympic-sized swimming pool. Okay? That pool doesn't leak. The water stays there. The reactor fuel looks the same as it did when we put it in. Because of the way the fuel is manufactured and the metal, the corrosion-resistant metal is put around the fuel, it looks exactly the same after 14 or 20 or 30 years of operation as it did when we put it in. And it doesn't leak because it's designed to keep all of the radioactive material inside the metal when it's operating in a period where the environment during an operating reactor is much, much hotter and much more stressful than when it's sitting in that nice cool pool and just being in retirement, enjoying itself, hanging out with its other cores. Okay? So I'm excited. I'm here to share you about that. And some people are afraid of nuclear energy, and there's a lot of reasons why. Here's my inspirations. And I brought the simulation here with me. If I had these 3 shooter marbles, if they were made of uranium, they'd weigh 1 pound. Okay? And if they were made of uranium, they'd have a total energy as much as what 30 tanker trucks could carry full of oil. 1 pound of uranium equals 30 tanker trucks full of oil. That's pretty inspiring when you think about it. One of the mantras of people who are really concerned about the environment is do more with less, right? You want to do more with less. Less material, less transportation is a big environmental benefit of nuclear. One of the biggest suppliers of uranium in the world is Australia. And Australia has exactly 3 mines. Actually, they may have added a 4th recently. But for a long time, Australia had a 3 mines policy. In the whole country, it's a big country, they only allowed uranium to be mined in 3 places, and they supplied 20% of the world's uranium, 25%. Okay? So the amount of material is pretty small. Next one. This is my second zero-emission vessel. That was the boat I was the chief engineer on, SSBN 632, USS von Steuben. And again, I told you a little bit about why submarine made me a strong supporter of nuclear energy. Because I really got up close and personal with the reactor. You have this? Oh yeah, that's fine. If you go down, I think there's that'll play. Here's a,
Oh, I see. All right, sorry.
no new sound. Just click on the next one, there's no problem.
I can.
Nah, it's not that big a deal. I'll send you all a link to that. It's a little, minute and a half, 2-minute video that explains why some people who are very strong, climate change scientists, one's a scientist and one's a consultant on climate change, and why they have decided to really like nuclear energy. We have big nuclear power plants in the U.S. This one's on the coast of California. It's the only one left in California, Diablo Canyon. As you can see, it's a pretty modest little site. It doesn't have any of those big cooling towers that people normally associate with nuclear because of the 3 Mile Island accident. You know, the cooling towers are just part of the steam plant. They're not really part of the nuclear plant. So this one sits on the ocean. It uses direct ocean cooling. And if anybody's ever been to California, you know that the water in California is really cold. And you all know, if you're mechanical engineers, that cold is good for a steam plant. It helps your efficiency go up. So they had a nice cold heat sink there. Go on. It's also possible with very small nuclear power plants. This is the NR-1, which is a research submarine, 400 tons, the entire ship, and it was driven by a small reactor. It was a very useful research vessel for a long time in the U.S. oceanographic area. It went down and found the Titanic and did a few other really neat things as it went through its career. A lot of its adventures are not yet known publicly. The U.S. Army, at one time in the early 1960s, said, you know, we've got a lot of small installations around the world, and we really have trouble delivering diesel fuel to them, so let's build some small reactors and power them. So we put one in Antarctica, we put one under the ice in Greenland, we put one in Alaska, a place called Fort Greely, we put one in Sundance, Wyoming. All of these places where it was really hard to get fuel to them. And then one of the Army's reactors was actually put inside a converted Liberty ship, drive down to Panama, and used for 10 years to power the pumps that raised and lowered the water in the locks in the Panama Canal Zone. But unfortunately, the Army nuclear power program, when they were looking at all these little reactors, these small things, and some of them pretty nice little machines, very reliable, built by a company called American Locomotive Company, which had built steam locomotives for a long time. They were doing a great job, but the Army ran out of funds when Lyndon Johnson said, we need to fight a war and we need to provide butter. So guns and butter, we don't have any room for nuclear research, Army. You go spend money in Vietnam and buy bullets. So the Army's nuclear power program ended in the early 60s. We built a ship called the NS Savannah. It was a beautiful ship. You can see this, probably one of the prettier cargo ships you've ever seen. It was built to carry 9,000 tons of cargo and 114 passengers in luxury staterooms with a swimming pool and a ballroom and beautiful. So it wasn't really built to make money. It was built to be a concept ship. It was an ambassador. It was a ship that was going to go around the world and say good things about the United States and its Atoms for Peace program. So for some odd reason, people say, well, the NS Savannah's failure as a commercial ship proves that commercial shipping is a bad market for nuclear power. Well, it was laid up in 1972 when the price of oil was less than $3 a barrel. If it would have operated one more year, it would have been operating in an environment where the price of oil was over $12 a barrel, and it suddenly would have been making money because the amount of oil that you burn in a cargo ship is pretty large. And then we still have, we have about 10 very large pieces of America that go around the ocean. This is the concept of the newest one, but they drive around on nuclear power, launch aircraft, go fast, go slow, and demonstrate the fact that nuclear power can be very responsive. It's not just baseload. Some people will tell you that it's just baseload power, it's just plants that start up and operate forever, but it's not. It can go up and down. But I've got some quotes from some influential climate scientists and environmental writers. George Monbiot is a British writer, very well known for writing about the environment, very strong environmental supporter. Anti-nuke up until the Fukushima accident. The Fukushima accident convinced Monbiot that, wait a minute, people have been lying to him. Because this disaster that everybody said was going to be a disaster, he said, wait, nobody got hurt from radiation. Certainly, since nobody got hurt, nobody died. And, you know, this catastrophe that was supposed to affect all of us is not affecting us all. So, and that was when this plant sitting on the coast of Japan got hit with the largest earthquake they'd ever experienced and a 45-foot high tidal wave. So he said, well, if it can survive that without hurting anybody, maybe it's not as bad as people have told me it is. He got into some discussions with people like Helen Caldecott and a few others, and has become a pretty strong supporter of nuclear energy, although he doesn't like the nuclear industry very much. James Hansen is one of the most famous climate scientists around, and he's also been going out and telling people, if you really want to do something about climate change, you need to accept the fact that nuclear is a tool that can help make the challenge easier to handle. It can provide you a better chance of winning. And if you don't accept nuclear and you say it's got to be all done with wind, solar, water, and wood, you're going to fail. James Lovelock, how many of you ever heard of James Lovelock? He was famous for describing the Earth as a natural system with feedback and actually working to keep itself in balance. They called it the Gaia theory. Okay? So Lovelock was a very leader of the environmental movement for a long time, was one that's looked up to as a guru until he started telling people in the environmental movement, and I put that in quotes or capital letters, as a group of people, not necessarily people who have a philosophy, but the environmental movement, when he started talking about nuclear, they said, wait a minute, James, you're getting too old and you're getting a little senile, we aren't going to talk to you about that stuff. Lovelock, by the way, is about 92 years old. Elon Musk, how many of you heard of Elon Musk? SpaceX, PayPal, Tesla, you know, he's a pretty big thinker, pretty advanced, and he says we need more nuclear plants so that we can charge his batteries. All right, here's some nuclear developments going on in the U.S. We're building some nuclear plants down in Georgia and South Carolina, 2 in Georgia, 2 in South Carolina. We also have one plant that was started back in 1974 called Watts-Bar 2, but it will probably be completed sometime in the next year. TBA has finally gone back and said, you know, these plants that we started up and got going pretty good, we really should finish them so they can start producing some electricity. But the 2 new plants are both AP 1000 designs, and I've got some friends that are working on them. They're going along reasonably well for first of a kind, but they've had some problems. They had a pretty significant delay at the very beginning when the Nuclear Regulatory Commission came in and said, we need all new plants that have not yet started construction to meet the aircraft impact assessment that we just passed as a result of 9/11. Since oil-filled airplanes were flown into tall buildings and a great big government building, we think that the nuclear plants around the country are very vulnerable. So we need to upgrade them to improve their ability to take a direct impact from a fuel-filled commercial airplane and make sure that they can still be safe in that instance. So they ended up spending about 18 months and $600 million redesigning the shield building. The rest of the reactor was maintained the same. Then very recently, and you guys are probably one of the first crowds I ever discussed this with, I just wrote about it on Saturday. Turns out that the people that designed the AP 1000 did something that I think is a very dangerous thing for an engineer to do. They said, we've been operating this particular type of pump, a canned motor pump, and we've got 50 years worth of experience in doing that, and they're very reliable, they work fine, last a long time. I'm pretty familiar with the technology from my background, but they said, and since we like those, we're going to use those in our newest plant. One problem that they did was, the experience that we have is at one size, the newest plant needed a capacity that was 10 to 20 times bigger. So they had to scale up this technology. And before they sold their first 8 units, they never tested the pump. They never built a full pump and tested it at full scale. They've got all kinds of models that say it's going to work, but it's not working so good. They've announced in 2010 that they had successfully tested the first unit. They announced in 2012 that they'd shipped the first pumps to China. In 2013, they had an impeller failure on a unit that was running in the U.S. A piece broke off of it after just a few hundred hours of running. Now, these pumps are supposed to last for 60 years. There's 8,760 hours in a year. And nuclear power plants are supposed to run most of those hours. About 8,000 hours a year at least. So do the math and figure out how many hours that pump is supposed to run. So they've got the defects reported. They've shipped, the pumps came all the way back from China to the U.S. Now, these aren't small pumps. 200,000 pounds or 91,000 kilograms. How many of you ever looked at the little, drive down the highway, you're a little bit bored, you're reading everything that's in front of you, and you look at a large truck going down the road, it tells you how much it weighs. The big trucks on a U.S. highway weigh 45,000 kilograms. 91,000 kilograms, twice as much weight as the big trucks on an American highway. So in order to transport this thing, you have to have a heavy lift truck. And moving it back from China to Western PA and back, not an easy task. That's what they had to do when they fixed it. And just in February, there was an article that said that, little teeny article said, well, we're working to redesign the pump. Now the first units in China were supposed to start up in 2013. The next scheduled date is the end of 2015, and the engineers are still redesigning the pump, which means they have to go back and retest it. They have to make sure, there's a whole lot of things they did when they just scaled up the design and said, we can also add a few little features to this pump. They added a big old flywheel to make sure the pump coasted down slowly. A massive amount of weight added to 2 different parts of the pump to make it coast down more slowly. I wonder if that has anything to do with the fact they're experiencing some failures. I don't know. But the scary thing to me is I'm a big nuclear advocate, and there's 8 AP1000 reactors under construction right now that can't operate without those pumps. So if you're an engineer, someone tells you, well, that thing that you worked on last year, it worked great, or you worked on 20 years ago, it worked great. Let's make it 10 times as big and sell it before we test it. Don't do that. Okay? New directions. I'm going to tell you a little bit about this project because it was one I was working on, and it was close to where you all are. It's only 30 minutes down the road in Lynchburg, Virginia. The B&W M-Power reactor. How many of you heard of it? Read about it in the paper?
Tiffany just started a job there.
I'm an intern there, yeah. I go there after I leave this talk.
Say again?
I'm an intern there currently, so.
Okay, so you're at the M-Power project?
Not the Empire project, just the.
Now,
Okay.
Rachel Rose, one of our recent graduates, out when she was interning, was working with him.
Okay, Rachel,
Rose, is it?
Yeah.
I think I knew Rachel. Can't remember.
And then I interned a few years back.
I left B&W at the end, September 2013. I worked there for 3 years on the project. It's a really nice little project, a nice reactor, and it's kind of pretty, and everything in the primary system is inside that single vessel. Really, but the company was spending about $80 million a year on it. Some new investors came in, bought a significant stake in the company. They're investors called activist investors, and they said, what can we do to make this company worth more money so we can turn it around and sell it? So we invested in stock, we're gonna make it worth more money when it's sell. So they said, well, you gotta improve the price earnings ratio. One of the best ways to improve the price earnings ratio is stop spending money. So they cut the budget for the Empower reactor from $80 million a year to $15 million a year. If you have people working for $80 million, the number of people you can work for $15 million is a little bit smaller than that. So the project size dropped dramatically. They're kind of in a holding pattern, and they're no longer a leading contender in the small modular reactor world. And I don't think they're hiring anymore. A lot of my neighbors work for B&W on the Empower project, and more than half of them have left Lynchburg at this point. All right, another small reactor is a NuScale power module, or a NuScale reactor. The power module is each individual unit. It's a smaller unit. It's only 50 megawatts per module, and each module has its own turbine generator. It's a complete power plant. It operates without any reactor coolant pumps. So they took another step. Instead of scaling up an old design and saying we're going to make a nice new design from an old design, they said, those reactor coolant pumps, they're kind of complicated. They're a little bit risky technology. If you scale it, they have to be reliable. Let's just get rid of them. So they make their plant operate. I'm just going to show you the size comparison. There's 126 NuScale power modules fit inside the container building, the AP1000. And those NuScale modules they're almost like a thermos. Familiar with how a thermos is designed? It's got an inner shell and then an outer shell. Well, that's how these are designed, with an inner shell and an outer shell, so they have their own containment with each module. So they don't need a great big building around it. They keep a second boundary by having just a second shell right around it. All right, the next slide, we'll go to the way a natural circulation reactor works is, if you heat something, it rises, right? So you heat it, it rises, then you create steam up the top, it gets that same water cold, it falls back down. And the reactor coolant circulates without any pumps. It makes it so that they don't need much electricity after they shut down. So if a NuScale power module experiences a complete loss of all electrical power, it has what they have trademarked as the triple crown of reactor safety. And with no operator action, no power, and no additional water, the reactors will shut themselves down, continue to circulate the water in them, use the water, they're installed inside a great big tank of water, use that water as coolant, and without any operator action, they'll cool themselves down and never melt, never have any problems. They're not going to release any reactor material out. Okay? So that's pretty neat little design. There's a lot of other innovation that's happening in the U.S. and North America because the large reactors have had some problems. They've not got good public relations. They're not doing very well on a business aspect. They're not competing very well against other sources. We haven't sold very many. Those 4 reactors that are under construction I talked to you about are the first 4 reactors that we've started since 1974, at least commercial reactors. We did continue building submarines and aircraft carriers. And of course, we built those in the U.S. with U.S. manufacturers. So, and some of them in Virginia, by the way. You all may be familiar, and at least one of you is, with the fact that the B&W plant just down the road, you can see it from 29 Bypass. It's been manufacturing stuff for the Navy for a long time. They even call it the Navy plant within B&W. Okay? Admiral Rickover liked Lynchburg because it was an easy drive for him to come down, visit the plant, and then go back up. He could do it in one day. Didn't have to spend the night. He could do other work. Okay, so General Electric is a very large company, $147 billion company with about $1 billion a year business in maintaining some of its old reactor plants. They haven't really pushed nuclear power in a long time. There was a time when GE thought that was one of their big growth businesses, but they kind of escaped that for a long time ago. And just before 9/11, Jeff Immelt, who runs GE, would have sold off the nuclear division if he could have found a buyer. But they do have a new design called the ESBWR. They're not pushing it very hard, but it's just getting a design certification. The staff finished their work, and the NRC should award it its design certification within the next couple of weeks. Holtec is a small company that does a lot of dry cast storage and other parts for nuclear. They're planning to build their own small reactor. Westinghouse has got a smaller version of the AP1000. GE's got a fast breeder reactor called the PRISM, which was based on a technology called the integral fast reactor, which has uranium as the primary fissile material. And as it operates, some of the neutrons that are left out convert uranium-238 into plutonium, which is also a fissile material and can be burned in a reactor. So the way that a breeder reactor works is it actually converts more fissile material into fuel than it uses up in fuel itself. So I like to think of it as the way that if you know much about building a fire, a campfire, you can go out and you can find very small pieces of wood that burn really easily. You call them kindling. And you take kindling and you get those built in a nice hot fire, and then you put some bigger logs around it or bigger sticks and get a bigger fire going. And then if you get a good hot fire going, you can actually burn wet wood. Well, that's how a breeder reactor works. It's get a good hot fire going and then turns wet wood, U-238, into fuel and continues to burn for a long time, as long as you keep moving the fuel around and keep doing things similar to what you would do to keep a campfire going. TerraPower is also a company that's a startup. TerraPower is an unusual startup because it's supported by two very rich guys, Bill Gates and Nathan Myhrvold, both who made a lot of money on Microsoft and other things. And they are funding TerraPower. They're working to develop a similar reactor, but a bigger one. And they've decided that since the U.S. has such a tough regulatory environment, they're going to go to China to build their first ones. It's kind of a disadvantage, disappointment to me. Transatomic Power is a neat little company. You guys may have read a little bit about Transatomic Power if you read some of the tech magazine and stuff. That the head of Transatomic Power, the CEO, is a young MIT PhD graduate named Leslie Dwan. And Leslie's been featured in Forbes 30, under 30 people, and she's a pretty sharp lady and very adamant that what her company is going to do is to take the used nuclear fuel, the stuff that everybody else calls waste, and convert it into fuel for her reactor. Their reactor is designed so they can operate with fuel that's enriched by about to 1.8%, which is the stuff that comes out of a conventional reactor and gets called waste. She says that's reusable fuel. It still contains 95% of its initial potential energy. Why are you throwing that stuff away? We want to use it. So it's a pretty interesting design, and she's getting some. She and her partner is a guy named Mark Massey. Flibe is a company that wants to build molten salt reactors that use thorium as the fertile material. Thorium's another actinide. How many scientists are in here? You know what an actinide is? A lot of people go glaze over when I don't like to try to, you have to list all the actinides. It's a group of metals: uranium, plutonium, thorium, americium, neptunium. All of those metals in that series are called actinides, and they're all potentially breakable, and they release a lot of energy when you break them. So Flibe likes to use thorium as their actinide, and thorium is actually 4 times as abundant in the Earth's crust as uranium is. So that's one of the things that they like about it. Terrestrial Energy has a molten salt reactor design, and Thorcon has also got a molten salt reactor design. And what they're aiming to is to produce a very simple, almost disposable design that reduces some of their material challenges. Okay? And some people ask who I work for. say, well, I'm a writer, but I also have these employers. And this is an aging picture because the two babies are now 18 months and 21 months. The lovely lady who's doing the filming is my wife, Jan, and that's who I work for, okay? And I really also try to tell people that I work for the American public because they were very generous to me. They sent me to college, they sent me to graduate school, they gave me a great job for about 30 plus years, and I want to thank all of you for doing that. And one more thing I want to give you as an inspiration. Anybody know what this is? I'll pass it around. Then I'll pass around some cards to tell you what it is. You guys have one, and then put one in the back row behind you. What it is a simulated fuel pellet. And whenever I pick one up, I feel very strong because it represents the amount of nuclear fuel for a conventional reactor that is equivalent to a full ton of coal, or 147 gallons of oil, or 17,000 cubic feet of natural gas. Okay, so that is another inspiration, something that helps me get really excited about the potential, the unrealized potential of nuclear energy. And now I'll ask for your questions. Who wants to start? I was told that you all asked a lot of good questions, hard questions.
I guess I'll ask a question. I feel like, especially oil and gas is our main energy source right now. What do you think the future entails for oil and gas transitioning to other renewable sources of energy, such as nuclear or solar or anything like that? How recent, like how long will it take?
Well, it's been taking a long time.
Yeah.
Okay, we've known about nuclear energy since, well, I guess it depends on how you date it. We recognize that if you could split uranium and cause a chain reaction. We learned that sometime around 1938, 39. We built our first self-sustaining chain reaction in December of 1942, and we haven't really taken too much of a market away from coal, oil, natural gas yet. Although we were making some pretty good progress. In the 1970s, the Energy Information Agency predicted that by 2000, if we continued at our present rate, we would have put coal out of business by 2000. Now, there are parts of me that say, if I was a coal guy and I read that prediction by my government that I was paying a lot of taxes to, and that I had, friends on Capitol Hill and also, friends in various state governments and all that, I would say, I don't like the idea of being put out of business by 2000. What can I do to slow this nuclear thing down? And so they did. They worked very hard. They actually formed an organization called the National Coal Policy Council, NCPC. It operated from 1957 to 1971. And throughout that time, this National Coal Policy Council was a very interesting coalition. It included coal mining companies, coal mine unions, or coal worker unions, electric utilities that burned coal, railroad companies, and coal mine equipment producers. That was the coalition. And they testified in front of Congress. They fought diligently against a lot of things that would have helped nuclear energy. They kept telling people that nuclear energy was less efficient. So that is one thing. There is some resistance from the coal and within the oil industry. The oil industry, their single largest customer in the 1960s and 70s was the U.S. Navy. We had a big Navy back then, and we were fighting a war. They didn't like the idea. Admiral Rickover wanted all of our ships to be nuclear. They worked hard to slow that down. There's a lot of things that we do with oil and gas that we can't do with nuclear. We cannot power a plane with a nuclear reactor. We tried. During the 1950s, we spent about $1 billion of 1950s dollars to research on something called the Aircraft Nuclear Propulsion Project, ANPP. It was not a success, and people figured out eventually, after spending a lot of money and paying a lot of salaries and building a lot of neat equipment and that kind of stuff, they figured out it's probably not a good idea. So we still going to need oil and gas for things like powering plants. We're going to need gas as a raw material. We're going to need oil for our cars, because although Elon Musk thought it's not so bad, you know, build electricity, make electricity, and then store it in a car and drive around long enough and then recharge your batteries. We've also been doing electric transportation for a long time. We call them trolleys and trains. Electric trains are still, if you go north in the train, how many of you live in the Northeast? What happens in Washington when you go north on a train? You change. You change from a diesel engine to electric. And the whole Northeast corridor is electric trains. So, you know, the subway is electric powered. You can use nuclear for electricity. Now, there are people, of course, who don't want that to happen, because selling oil and gas is a great business. ExxonMobil has an annual revenue, well, before the price of oil dropped dramatically, to 2014, they were making their revenue was about $450 billion a year. That's 3 times the U.S. Navy's budget, total budget, for one company. So oil and gas have resisted the transition for good reasons, but yes.
I guess I have 2 questions. So my dad was in the power plant, and I thought frequently we talked about plenty, trying to power plant with nuclear power, and he had always told me that it was basically because you couldn't get a light enough weight reactor to make it feasible. Do you think with the upcoming reactors that could potentially change?
The thing that makes nuclear heavy per unit power to the point where it's possible, but the thing that makes it heavy is you've got to surround it with a lot of shielding. You've got to have material that's really dense to stop the gammas that get produced in the reactor. You have to have material that has a lot of hydrogen in it, usually plastic or water, or hydrogen or other hydrogenated materials, to stop the neutrons that get leaked out. And when you build that layer of shielding, it's just heavy. Even if you've got a fairly small reactor, you've got to have a lot of weight around it. Now, for ships, the weight and space required by a nuclear plant is far less than the weight and space required for an oil plant if you include the fuel tanks. Okay? The nice thing about the reactor is, I told you how big our fuel tank was, right? It was the heat source and the fuel tank. Not very big. And if you've ever taken a look, there's some beautiful pictures of what a nuclear reactor power plant looks like. And it has the reactor and the buildings, and the reactor is a really tiny portion. It's almost hard to find it. So the fuel tanks aren't very big. So with a ship, you know, it's much more compact. If you need to travel more than about 5 days. Once you go beyond 5-day duration, nuclear is more compact than an oil, even a good gas turbine ship plus its fuel tanks. Yes?
Again, what happens to the brains? Because we know that they have reactions here, they have radiations here.
Yes?
So what happens to the brains?
We store it right now. We put it into a container and we let it sit. Okay? Now, it's still radioactive, but it's getting less radioactive every day. That's one of the things that's how radiation works, right? Things that are very radioactive and very dangerous are things that decay fast. They have a short half-life and they give off their activity very quickly. So the things that are most radioactive in that fuel decay away as it sits there in its shielded container. And it gets less and less radioactive over time. Now, the stuff that's not very radioactive, the stuff that has a very long half-life, the stuff that people say, well, we have to watch this stuff for hundreds of thousands of years because it's got a very long half-life, that's mostly actinide material. It's mostly plutonium and uranium-238, which actually has a half-life of over 1 billion years, it's that material is what is causing the concern. So my answer to that is, I don't want to store that. I want to take that and give it to Leslie Dwan or to Transatomic Power, or somebody else who's going to make use of that material as fuel. Okay? Yes, it's dangerous, but so are a lot of things that I have in my garage. As long as I keep them in the container, the appropriate container, if I keep the gasoline in little plastic containers, if I keep my paint in the right container, it's not dangerous. It's only dangerous if I let it out. And as far as I know, and I've been searching now for 20 years, there has not been a single instance anywhere in the world where someone has been harmed by being exposed to used nuclear fuel. Yes, there have been a few instances where people found a radiation source for medical sterilization and got hurt because they broke open the source and they thought it was cool to play with the little glowing metal. It was cesium-137, by the way. And they actually ate it. It was 240 people got significantly exposed. 4 of them died. And it was placed in, I think, in South America, Brazil, maybe. I may be getting it wrong, but nobody's ever done that with used nuclear fuel because we know where it is. We put it in big sealed containers. We have people that look at it now and again. We put it behind fences. We protect it because we know that it has some value, and we know that we have to. There's regulations that keep us to protect it. So we can count all of the waste material that we've ever produced. Now, I like to ask people who compete with me, what do you do with your waste? What does the coal industry do with its waste? Is any of that waste deadly? Is any of that waste damaging the environment? I mean, even if you don't count all the stuff they throw in the air, have you ever seen the ash pile next to a coal plant? How many of you remember what happened in Tennessee Valley Authority maybe 2 or 3 years ago where they had a coal impoundment break open and 9 million, I don't remember the number, but it was a huge amount of material that came out of that coal story and flooded the town with this gray, silty stuff. Didn't we have one of those nearby here on the Dan River? Wasn't there a leak from one of the coal?
Train.
No, that was there was the train that overturned in Lynchburg, which was carrying oil, but the Dan River back in beginning of 2014 had a leak from an old decommissioned Duke Power coal plant that filled the river full of gray ash and was big news in Danville. But,
That took a lot of North Carolina. I know it was a big deal there.
well, certainly the Dan River's a border, right, between North Carolina and Virginia, I think, in parts of it, and it was a big deal because it was going downstream and affecting people in North Carolina. It's a source of drinking water, fishing, all that stuff. So there's waste problems in all power sources. I think we do a pretty good job.
I think with, when we do deep water drilling, I'm not sure if we're fracking, but deep water drilling, when the gas, oil and gas comes up, a lot of harmful gases do as well, and you have to burn the gas off immediately. And so that's why when you see on deep water platform, you'll see a fire going off of it.
Right,
Because it's
flares.
it's burning off the gas.
Now, interestingly enough, with, you all have heard about fracking and the fact that we've found new oil sources in the U.S. Our oil production is improving, increasing from the Eagle Ford Shale, from the Bakken, and those tight oil reservoirs, we use fracking not to get gas, but to get oil. And because both the Eagle Ford Shale and the Bakken were not traditional oil-producing regions, they don't have much pipeline. Okay? So they're transporting their oil via trains, but when you frack and get the oil out of those wells, you also get natural gas, which is great stuff if you can contain it and pipe it to a customer. But if you can't contain it, you better get rid of it some other way, because it's methane that is explosive. You know, if you don't get rid, so there are big flares in southeast Texas and North Dakota, which make them light up like they're a big city from the sky. If you're looking at it from a satellite picture, those flares are looking like, hey, wait a minute, this great big city just sprung up in North Dakota. Not from people, it's from gas flares. So, you know, that's a waste, you know. And again, for me, that's good fuel. I mean, natural gas is good stuff. I like having natural gas. I don't think it's a good idea to waste it by flaring it off. But I guess it's better than killing people.
Okay, people gotta go to class pretty soon, right?
Yeah. Well, thank you all for your attention. I hope you all enjoyed your pizza. And if any of you want a card, so you can find my website, and this is a note from our sponsor. My employers want you to visit.